Hello, my name is Jessica Boyd and I will be presenting on KI number 5, or Knowledge Integration number 5. This is part number 2 of Signals and Transmissions. Since I am a part of all 3 ECE classes, Microelectronics, Electromagnetics, and Signals and Systems, I will be incorporating all of their information in our exploration. A cell phone will continue to serve as our reference example as it did in KI number 4. To refresh your memory, KI number 4 explored how signals are transmitted. Now for KI number 5, we're going to focus on how signals are received. So KI number 4 focused on the top level of the block diagram, and now we will be focusing on the red aspect. You'll notice when analyzing this top level block diagram that the first electronic element we encounter is the antenna for the receiving portion. Antennas can be constructed in a wide variety of ways, but one of the most popular ways to design an antenna is a PCB antenna, or a printed circuit board antenna, as these diagrams kind of illustrate. One of the most important highlighted aspects in this design is the matching network, right here. Now, the matching network matches impedances in order to ensure maximum power transfer. Maximum power transfer both maximizes efficiency and protects the circuit. If impedances are not matched, the circuit will see a reflected wave, which will build standing waves on the transmission line between the source and the load. The incident wave and the reflected wave will subtract or add depending on the phase difference. So some places on the line will equal 0 volts and maximum current. Large current results in more thermal energy that can destroy the MOSFET transistor. The impedance that we encountered was 50 ohms. This can be specifically calculated using electromagnetic wave equations and not neglecting fringing effects. Or it can be interpreted from your intuition. As we've acknowledged several times in ECE 332, almost all wire transmission lines are around 50 ohms. Now continuing on through our circuit, we see that we're running into a bandpass filter and a low noise amplifier. As we already know, a bandpass filter only allows a specific range of signals to enter, and a low noise amplifier does not significantly degrade the noise to signal ratio. Therefore, it's hoping to amplify a signal that has low noise. As we walk through the different circuit elements, we know that the primary goals in general design includes increasing the swing, increasing the gain, increasing the bandwidth, decreasing the size, decreasing noise, and decreasing power consumption. Some of our knobs that allow us to do all of these different desired goals is changing IDS, changing W and L, or the W over L ratio, changing VSAT, and changing VDD, just to keep in mind as we walk through this design. As for our bandpass filter and our low noise amplifier, this is our circuit. Obviously we can tell from a glance because you look at it and you say, oh, capacitor. Capacitors are open in DC range, low frequency, and act as shorts in high frequency. Therefore, at low frequency, this will be turned off. And then at high frequency, or this will just remain 0, and at high frequency, these will be shorted. So, if we take our capacitor and our resistor and change them into their equivalent impedances, then we can combine them in parallel and combine them in series and represent them as this circuit. Our op-amp with our differential input pair and our single output. Now, taking this squished version, we can recognize it as an ideal op-amp. For an ideal op-amp, there is infinite gain, which means that the input voltages are exactly the same. There is no current that enters the op-amp. Because these input voltages are exactly the same, we assume that this guy is also 0. So when we go to carry out our nodal analysis, as done in this situation, this current equals this current, and setting up our V-ins and V-outs, then we set this to 0 and we get our equivalent gain result, which also makes sense because it's negative, and it's going into the negative input terminal, so it's an inverting amplifier. What happens if it's non-ideal? Non-ideal can make it much more complicated, because now as we transition through the circuit, our V minus can no longer be interpreted as 0. In this case, we were given that the gain was a situation of A over 1 plus ST. Therefore, the pole is at T over 1 over T. So, if you were struggling at all through this math, you go through and you do the normal nodal analysis, and then you divide them over, as this should all explain, and then you use the given equation that V out equals A times V plus minus V minus. We know that V plus is for sure 0 in this case, but V minus is now our V1. So we take our simplified equation for V1 here and plug it in and continue. I don't think I need to walk through the math since you're all brilliant engineers, but I get this simplified result. Now for my bandpass filter, I simply define what my Z in and my Z out are, and I have my, again, simplified result. So when I go into MATLAB and I want to see how these are actually performing, I can compare the difference between the ideal and the non-ideal. As you can see, this one's a lot more ugly. Definitely lets in a wider range, which is not what we want, definitely not desired. So continuing on through our system, we see that after the bandpass filter and the low noise amplifier, we have a mixer. And the mixer is mixed with a low frequency signal. Makes sense now that it's low. That low frequency signal can be used or can be created by what's called an oscillator. Sometimes circuit designers like to use crystals as well, but in our lab we explored oscillators. An oscillator can be created by a simple LC circuit, and we can go through and derive the different poles and transfer functions of this LC, doing, ECE 202 second order differential equations. Of course, having only an L and a C is very idealistic and not very real world, because there is always resistance in every element that we interact with, especially wires. So how do we work with this resistance and how do we counteract it? When we add a resistance into the signal, it definitely changes our transfer function into a more complex and complicated circuit, where now we have to use a quadratic equation to identify what our poles are going to be. But we can see the DC gain in the numerator. You see I'm fudging, so hopefully we're having no technical difficulties because we've had a lot today. Anyway, when thinking about the poles and where they're located, I attempted to counteract the resistance added from the wires by incorporating another capacitor in series. Capacitors in series combine like resistors do in parallel. Therefore, you could decrease the capacitance, and decreasing the capacitance would allow you to counteract the increase in resistance. I tried to avoid including more inductors as much as possible, although I considered adding one in parallel, because inductors can be very, very large. You can use ferrite beads to make up for this, but they are very expensive. And then just to refer back, the mixer mixes the two signals and it transfers energy and frequency. Continuing on our block diagram, we enter another op-amp and our low-pass filter. Our low-pass filter works in exactly the same way. We combine these in their equivalent Z out and their equivalent Z in. And then we compare them in MATLAB, and we can see obviously how it's impacted by the internal pole that's in the op-amp, because an ideal op-amp has infinite gain and no poles. So that was the entire design. I wish I could have discussed more, but there was a lot to cover. Thank you so much for listening.